input, that is 0 to dn minus 1. The input is an n-bit binary word S, that is S0 to Sn minus 1. But in chip, it is mentioned in D0 to Dn minus 1, that called the data input. Okay. Here, this is the signal input. For this is in S in a broader sense. And for a particular IC, it is nomenclature as the data. So for this reason, this is D0 to Dn minus 1. So you can write as S0 to Sn minus 1 or D0 to Dn minus 1. No problem. The output of a DAC can be either a voltage or a current. I already told in the previous class. The schematic of the DAC is shown in the figure. This is the analog output with respect to the given digital input. Okay. So this is the VA. This is the in general form. This is VA is equal to K, where K is the proportional constant with respect to the reference voltage VR. I will come to the better design, the internal design of the weighted binary resistor, then you will be understand. So K is Sn minus 1 into 2 to the power of n minus 1. We will get from the circuit of this general expression. So for any competitive exam, you should remember this. That is K into Sn minus 1 into 2 to the power of n minus 1 plus Sn minus 2 to the power of n minus 2 to S0 to the power of 0. Okay. So in general, that is VA is equal to K into summation of K is equal to 0 to n minus 1. This is the small k, this is the capital K. Capital K is the proportional to the reference voltage. This is a separate expression are there. I will come later. So, and this is the bit K0 to Kn n minus 1 Sk to the power of n to the power of K. Okay. So its value depends on how the DAC is implemented. Now, if we come to the very basic internal structure of the weighted binary register DAC, this is nothing but a summing amplifier principle. Already you know in the basic electronics class, this is the op-amp summing amplifier. So by connecting the multiple inputs to the negative terminal, this is the negative terminal of the operational amplifier, we can convert the single input circuit from the above into a summing amplifier, or to be more precise, a summing inverter voltage amplifier circuit. Okay. So suppose this is the ground, this is the virtual ground. So now if the voltage of this or the I4 current, so then we will get the V in 4 minus V0 by R4 equal to I4. So then you will get similarly for I1, I2, I3 and I4. Now the feedback current IF is the summing of the I1, I2, I3 and I4. Okay. So then you will get, this is V0 minus V out by RF is equal to IF. So this is the basic principle of the summing amplifier. As the negative feedback created by the feedback resistor RF biases the inverting input of the op-amp at 0 potential, any input signals are effectively electrically isolated from each other, with the output being the inverted sum of all the input signals. So this is a inverting amplifier. Okay. So if this is a inverting amplifier, so then we will write the V0 is equal to RF by R1 minus into V in. This is the, actually this is minus. So this is the for inverting amplifier output. V0 is equal to minus RF by R1 into V in. So here we will write, this is a summing, this is an inverting voltage amplifier. Okay. So now thus the summing amplifier in the inverting mode produces the negative sum of any number of input voltages, whereas no inverting summing amplifier would produce the positive sum of the number of input voltages, as we know from the basic electronics, that for the inverting amplifier the output is negative, and for the non-inverting the output is positive. Now if we go to the elaboration of this circuit, that this is IF is equal to I1, IF is equal to the summer of the I1, I2, I3 and I4, summer of the I1, I2, I3 and I4. So then the I1 would be V in minus V0 if this is a V0. So then V in minus V0 by R1. As V0 is equal to 0 for virtual ground, then we can write I1 is equal to V in by R1. I2 is equal to V in 2 by R2. I3 is equal to V in 3 by R3. Similarly for I4, V in 4 by R4. Now add. So IF is equal to I1, I2, I3, I4 is equal to V in by R1, V in 2 by R2, V in 3 by R3 plus V in 4 by R4. Now come to the V out. So as simple as V out is equal to minus RF into IF. This is an inverting amplifier, so for this reason this is minus. Now the V out is equal to IF into RF, or we can write V0 minus V out by RF is equal to IF. Okay, so V out is equal to V0 is 0. So V out is equal to minus IF into RF. Okay, so I just allow someone admit. So now come to the part of the V out is equal to minus RF into IF is equal to minus RF by R1 V in 1, RF by R2 V in 2, RF by R3 V in 3, RF by R4 I in 4. So now if RF is equal to R1, R2, R3, R4 is equal to R in general, then we can write V out is equal to minus RF by R in, V in 1, V in 2, V in 3, V in 4. This RF by R1 is the amplification factor. Okay. So now when we can see that the output voltage is an inverted, scaled means RF by R1, this is a fraction should be there. If RF is equal to R1, then it will be 1. Otherwise there will be some fraction, so it will be scaled down. So the scale sum of the 4 input voltages, as each input voltage is multiplied by its corresponding gain, this is the gain, and added to the next to produce the total in output. If all the resistance are the same, as simple as R1, R2, R3, R4 is equal to the R in, all the resistance are same and of an equal value, that is RF is equal to R1, R2, R3 is equal to R4, then each input channel will have a closed loop voltage gain of unity. If RF is equal to R in, then this is a unit gain amplifier. So the output voltage is given simply by V out is equal to, if RF is equal to R in, then V out is equal to nothing but a summation of all the input voltages V in, V in 2, V in 3, V in 4. Clear? So now if we go to the weighted binary register, it is nothing but this is a reference voltage VR. This is the S0, this is the LSB. Suppose this is a 1001. This is LSB, this is MSB. So S0 is equal to 1, S1 is equal to 0, S2 is equal to 0, and S3 is equal to 1. Here the input voltages are the weighted input voltage. For this reason it is called weighted binary register. So now if for a 4-bit binary number there are 2 to the power of 4, that is equal to 16 possible combinations of A0, A1, A2 and A3. This is the A0, A1, A2 and A3. These are the input voltages A0, A1, A2 and A3. So what will be the combination of this A0, A1, A2, A3 is nothing but this is a A0, this is the A1, this is the A2 and this is the A3. Okay. So the A0 is nothing but a S0 into VR. If S0 is 1, then what is the A0? That is the VR. If this is S1 is equal to 0, what is the value of A1? Now it is 0. If it is S2 is 0, so the A2 will be 0. If this is S3 is 1, so the A3 is VR. So this combination of A0, A1, A2 and A3, we will get 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, 1, 1, 1, 1. So that will be the value. So what will be the value? Input voltage 0, 0, 0, 0, 2, 1, 1, 1, 1. So for this reason, this A0, A1, A2, A3 should be ranging from 0, 0, 0, 0 to 1, 1, 1, 1, which corresponds to the decimal value is 0 to 15 respectively at the output of this weighted binary DAC. If we make the weight of each input bit double with respect to the other, please go through this line. If we make the weight of each input bit double with respect to the other, we end up with the 8421 binary code ratio corresponding to 2 to the power of 0, 1, 2 to the power of 2, 2 to the power of 1, 2, 2 to the power of 2, 4, 2 to the power of 3, 8. So this is a binary number. Okay. 8421 basis. So if we set the A3 input resistance at 1 kilo ohm, then A2 input resistance should be 2 kilo ohm. Okay. So this is the MSB A3. So this is the 1 kilo ohm. Then A2 should be 2 kilo ohm. R1 should be 4 kilo ohm. Or R0 should be 8 kilo ohm, because this V or this is the I. So I means S3 VR by R3. So if R3 is 1, then we will get, if R3 is less, then we will get the large number of current. So this is the MSB. So for this reason it will be large. So for this reason this R should be less. Clear to you? This MSB resistance should be less due to the high resistance, high current at MSB. Because if we put MSB as 1, then it will be larger than if we put the LSB is 1. So for this reason, the MSB current, that is called I3, should be greater than the I0. So for this reason, the R corresponding to the MSB should be less and LSB should be higher. So for this reason we set R3 as 1, R2 as 2 on that basis. R2 is 2, R1 is 4, R0 is 8. So very simple. The I should be, this is the I, total I. So I should be the summation of I1, I2, I3 and I4. So this is the I1, this is the I2, this is the I3, this is the I4. So that means the S3 VR by R3, S2 VR by R2, S1 VR by R1 and S0 VR by R0. So if the V out is I into RF, I into RF and the inverting terminal here. So this is a inverting amplifier. So for this reason V out should be minus RF into I. So nothing but a V out is equal to minus RF S3 VR by R3, RF S2 VR by R2, RF S1 VR by R1 and RF S0 VR by R0. So very simple, we can write if the R3 is equal to 1 kilo ohm is equal to R, then R2 should be twice R, R1 should be 4R and R0 should be 8R. So put here. So that is RF S3 VR by 1R, RF S2 VR by 2R, RF S1 VR by 4R, RF S0 VR by 8R. Now if I take common as RF by R into VR, then we will get minus RF VR by R into S3 by 2 to the power 0, S2 by 2 to the power 1, S1 by 2 to the power 2, this is 4, so that means 2 to the power of 2, S0 by 8, that means 2 to the power of 3. Now if we take common as 2 to the power of 3, then we will write S3 2 to the power of 3, because 2 to the power of 0 is equal to 1. So then we can write S3 2 to the power of 3, S2 2 to the power of 2, S1 2 to the power of 1, S0 2 to the power of 0. So in general, we can write like this. If S0, S1, S2, S3 is equal to 0, 0, 0, 0 to 1, 1, 1, 1, then we will get using this formula, that is minus RF by R into 2 to the power of 3 into VR, S3 2 to the power of 3, S2 2 to the power of 2, S1 2 to the power of 1, S0 2 to the power of 0. Put the value here, S0, S1, S2, S3, all are the 0. So then we will get 0 voltage at the output. If we put S3 is equal to 0, S2 0, S1 0 and S0 1, then only we will get 1 by 8 to the power of 3, that means 8. RF by R is equal to 1. So now this we will get 0 into VR is equal to 5 volt for digital electronics. So VR is equal to 5 volt. So 0 into 5 plus 0 into 5 plus 0 into 5 plus 1 by 8 into 5. So the output voltage is almost minus 0.625 volt. So what will be the DAC? The DAC input is the digital input 0001. What will be the value of the output? The minus 0.625 volt. Okay. So similarly, if all are the 1, so that is 1, 1, 1, 1. Then put 1 into 1 into 5, then 2 to the power of 1. So 1 by 2 into 5, then 1 by 2 to the power of 2, then means 5. So 1 by 8 into 5. So then we will get this voltage. So the corresponding input of the 1111, we will get the output voltage is minus 9.375. So this is the in general formula. So if we in general it for an n bit DAC, then we can write for an n bit DAC, we can write RF by VR by R into 2 to the power of n minus 1 S n minus 1 to the power of n minus 1, because here the n is equal to 4 for a 4-bit DAC. So if this is n is equal to 4, then we can write in general minus RF into VR by R into 2 to the power of n minus 1 into 2 to the power of n minus 1 into S n minus 1 plus S n minus 2 into 2 to the power of n minus 2, like this we can write. So if in general we can write, if V of AK means this is A0, A1, A2, A3. So K is equal to 0 to n minus 1. So that means V of AK is equal to SK into VR. So now V of AK, suppose this is a 0. So K is equal to 0. Then we will write S0 into VR. If this is 1, so then we can write S1 into VR. If it is 2, then S2 into VR. If it is 3, then it is S3 into VR. So very simple. This is a K. K is nothing but, small k is nothing but n minus 1. So this is 0 to n minus 1. So k value should be 0 to n minus 1. So the IK will be V of AK minus 0 by RK in general. So then we will write RK is equal to 2 to the power of n minus 1 R by 2 to the power of K. So then we will get VR by 2 to the power of n minus 1 into R, 0 to n minus 1 SK 2 to the power of K. So very simple. So V0 is equal to minus RF into I. So this is minus VR RF by 2 to the power of n minus 1 into R, 0 to n minus 1 SK 2 to the power of K. So देखो, in previous section this is minus RF by VR R into 2 to the power of n minus 1, then S n minus 1 to 2 to the power of n minus 1 plus S n minus 2 into 2 to the power of n minus 2 like this. So this is the K is nothing but a 0 to n minus 1. So then we can write like this. So this is a general formula of n-bit DAC, capital n-bit DAC. Okay. So if it is a 4-bit, then we can write 2 to the power of 4 minus 1, that means 3. So minus VR RF 2 to the power of 3 into R, 0 to 3, n is equal to 4. So 0 to 3 SK 2 to the power of K. So that means S0 2 to the power of 0, S1 2 to the power of 1 plus S2 2 to the power of 2 plus S3 2 to the power of 3. So now if we go for an example, then it will be very clear. Suppose this is a 8-bit DAC. Then what will be the value of n? N is equal to 8. VR is equal to 5. What is the smallest value of R which will limit the current drawn from the supply VR to 10 milliampere? So maximum is 10 milliampere. Okay. So if we get all nodes A0 to A7, because this is a 8-bit DAC, so the K should be 0 to 7. So then we will get A0 to A7. So this is, we will get A0 to A7. So R7 should be R. Okay. So R6 should be twice R. R5 should be 4R, like this. So the R0 should be 2 to the power of 7R. So then we will get the maximum current, that means I is equal to 10 milliampere. This is the I. This is the I. The maximum current 10 milliampere is equal to VR. This is the S0 to S7. So the input voltage is, this is S0 VR and this is the S7 VR. Okay, so now all are the one, maximum current. So this is the all are the one. So that means S0 to S7 all are the one, or all are the connected to VR. So then we will get VR by R, VR by twice R to VR by 2 to the power of 7R. So then we will get, according to the formula, the 1 by 2 to the power 7 VR by R 2 to the power of 0. That because this is a S0 2 to the power of 0, S1 2 to the power of 1, to S7 2 to the power of 7. So all are the 1, that means S0 to S7 should be 1. So for this reason we will get this. Okay, so here we know the VR 5 volt. So then from this we will get the R minimum volt resistance is equal to 996. So if it is R, then we will design like this: R0 is equal to 2 to the power 7 R. That means 2 to the power 7 into 996 ohm. Then this is 2 to the power of 6 into 996 ohm, and this is the 996 ohm. So we will design this DAC according to our target. Okay, বোঝা গেছে এটা?
सर हेलो
बोलो।
सर, अनेक वेटिंग रूम में कब से वेट कर रहा है सर, और ढुक नहीं पाया।
ओके 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 ओके। So this is the total R minimum value of the 996 ohm. So now if we go to the next problem, consider the 8-bit DAC. That means N is equal to 8, N is equal to 8, VR is equal to 5 volt. If RF is equal to R, then what is the resolution? The concept should be applied from the previous class. So if RF is equal to R, what is the resolution? Resolution means VA corresponding to the, এখনো ঢুকলে কি করে হবে, ক্লাস তো শেষের পথে। VA corresponding to the input LSB changing from 0 to 1 with other input bits constant. So now VA is equal to, from the formula, this is the VA, output voltage. So output voltage, we can write the formula like this from the previous section: minus VR RF by 2 to the power of n minus 1 R. This is the value of the capital K from the first slide, the proportionality constant with respect to the RF and the VR. Okay, so this is the capital K, this is the small k. Small k is the 0 to 7, that means 0 to n minus 1, and capital K is the proportionality constant and nothing but a resolution. If you go through the formula of the resolution, then you will get this. So this is the capital K is nothing but a resolution minus VR RF by 2 to the power of n minus 1 into R for the DAC, and this is the weighted output. So that is S7 2 to the power of 7, S1 2 to the power of 1, to S0 2 to the power of 0. So in between, depending upon the value of S1 to S0, we will get this. Okay, so now this is called the delta VA or the capital K. We will get the value of this. So now if we put the maximum VA means all should be 1, S0, S1, S2, S7 should be 1 for the maximum output. The maximum output if we get, or all 1. Okay, So this is the maximum of, oh, this is extra bit. So all 1. So this is the all 1 should be as the input. Then we will get the maximum output. So for this reason, we can write this 5 by 128 into VR, no, sorry, 1 kilo ohm resistance. This is RF by R. Very simple, for RF by R is a unit gain amplifier. So RF by R is equal to 1. Then we will put S0 to S7 as 1. So then we will get 2 to the power 0 plus 2 to the power 1 plus 2 to the power 7. So then this is the final output voltage. Okay. The resolution is this. What is the percentage of resolution? 3.91%. Please keep in mind for any competitive exam, the DAC, for the n bit DAC, the resolution should be VR by 2 to the power of n minus 1 RF by R. If RF is equal to R, then this is the resolution. Okay. So now come to the another problem. Suppose the 8-bit DAC has the resolution is 10 millivolt per bit. It is given. Okay. Find the analog output voltage for the input is this. This is the K. Okay. The resolution. So very simple. We will write the V0 is equal to nothing but a, V0 is the output, nothing but a K into weighted output. So here the weighted output is like this, because we will get V0 is equal to minus delta VA or the K into the D. I know. So V0 is equal to minus delta VA or K into D. D is this, the weighted output. So put the value of D for the input is this. So S0 is 0, S1 is 1, S2 is 0, S3 is 1, S4 is 0, S5 is, sorry, S5 is 0, S6 is 0, S7 is 1. So put here 1, 0, 0, 0, then 1, then 0, then 1, then 0. Then we will get the value of this. So the V0 is nothing but mod of this delta VA. Delta VA is the resolution. So 10 millivolt into 138. So V0 is equal to 138 into 10 millivolt per bit is equal to 1.38 voltage. So for the output of this, put the value like this. S0 is 0, S0, S1 is 0, S2 is 0, S3 is 0, S4 is 1 and all others are 0. So only the S4 into 2 to the power of 4. Sorry, 0, 1, 2, 3, 5. S5 into 2 to the power of 5. So S5 into 2 to the power of 5. So this is 32. So now the V0 is equal to 32 into K. So then we will get this. Got my point?
Yes, sir.
Very good. So now come to the another type of problem. I tried to explain different types of problem which are in the gate. Consider an 8-bit DAC with VR is equal to 5 volt. Find the output voltage corresponding to the input. Then come to the, if the resistors are specified to have a tolerance of 1%, so maximum value and minimum value we should calculate. What is the range of VA corresponding to the input of this? So now first come to the first portion of the problem. Find the output voltage corresponding to the input of this. and this is the 8-bit ADC DAC. So that means capital N should be 8 and VR is equal to 5 volt. So put the value here, minus VR by 2 to the power of n minus 1 RF by R, S7 into 2 to the power of 7 to S0 into 2 to the power of 0. Put the value of S0, S1, S2, S3 to S7 like this. This is the S0, S1, S2, S3, S4, S5, S6, S7. So put here. So then we will get only 0, 2, 3, 5 and 7. 0, 2, 3, 5 and 7. 0, 1, 2, 3, yeah. 0, 1, 0, 2, 3, 5 and 7. Okay. 0, 2, 3, 5 and 7. And this is the VR by 2 to the power of n minus 1. That means 2 to the power of 7. So that is 128. RF by R should be 1. So then we will get this voltage. So this is the VA at the point of this and at the point of this finally. So this is the VA, the output voltage. This is the proportionality constant K or the resolution. Okay. So now VA is maximum when the currents I0, I1, etc. That means I0 to I1 to I7 assume their maximum values with the RK into tolerance. So the maximum, this is the VA is the maximum. So RF should be the maximum is this and R minimum should be maximum of this because the tolerance is 1%. That means R plus minus 1%. Okay. So R minimum should be R minus 1% and R maximum should be R plus 1%. That is written over here. This is the minimum. This is the minimum and this is the maximum. Okay. So this is the minimum. For this reason, this is minus. That means R minus 0.01%, 0.01. That means 1%. R, this is the maximum. R 1 plus 0.01. That means 1%. So R range should be R plus minus 1%. So this is plus, this is minus. Minus for minimum, plus for maximum. So if we know the RF, then we will write this. Very simple. So VR is equal to 255 by 128. Okay. RF by R. Sorry. RF by R. So then we will get why it is 255. Can you tell me why it is 255? This is the maximum step size. 2 to the power of 8. 0 to 2 to the power of 8. So what will be the steps? Number of steps? 255. Right now? 0 to what is the full scale? 255. What is the full scale? 255. So for this reason, this is the full scale value. 255 by 128, 2 to the power of n minus 1 into RF by R. Okay. So now RF is equal to, this is the maximum. This is the maximum. So RF should be 1.01 maximum value and R should be minimum value. Then we will get the maximum proportion. If it is maximum, then what will be the proportion maximum value? RF should be maximum, R should be minimum. So R should be maximum means 1.1 plus 0.1. So RF by R is equal to 1 plus 0.01. So that is 1 plus 0.1. And R minimum is 1 minus 0.01. So that means 0.99. Similarly, for VA minimum, this should be minimum. That means RF should be minimum. R should be maximum. So RF should be minimum means 0.99. Maximum means 1.01. So this is the maximum value. This is the minimum value. So now for delta VA, the change of the maximum to minimum, this is 10.162 minus 9.764. So what will be the value? 0.4 volt. Okay. So now the resolution is nothing but a VR by 2 to the power of n minus 1 RF by R. So we will get the resolution is 0.4%. So if this is a 0.04, if we will calculate this as RF by R is equal to 1, so if we put this VR by 2 to the power of n minus 1, then we will get the actual resolution, and that will be like this. So here in our designed DAC, the resolution is approximately 0.4 volt. But in practical, it should be 0.039. So 0.4 is higher than 0.039. So it is not acceptable. So for this reason, we should choose the R2R ladder network instead of the weighted binary register DAC, because the practical resolution is the higher with the ideal resolution of the weighted binary register, which is not desirable. So for this reason, we should go for the R2R ladder network or R2R weighted binary register network, okay, DAC, which I will discuss on Monday evening. Because, okay, why it is Monday evening? I just stop the recording.